chapter 2. We will be okay. Okay. Now today we're going to look at Aquarius corrosion. So I'll be using these 3 books, additional with this book. So in this chapter 2, we will cover what is potential pH diagram, and then the application of potential pH diagram, and then we look at corrosion of steel in the elevated temperature for reinforced steel. So this one, yeah, we see how if we have time, we include this one, right? Then we look at Filliform corrosion. We look at kinetic principle and kinetic equilibrium. All right. So you can download the tutorial question from the Moodle. All right. So just to follow along, and you can fill in the blank space there. Okay. All right. First, when we talk about corrosion or Aquarius corrosion, the starting point we need to ask ourselves is how Aquarius corrosion happen. So we start with how corrosion happen. One of the factor is environment. So environment means beside the metal, what happened around the metals or alloys that contribute to the initiation of corrosion process. Again, in chapter 1, we already cover corrosion happen is without external electricity. Yeah? So if you add external electricity to the system, then you are having electrolysis process. Then it will not fall under corrosion. Corrosion happen within itself and its own system, where metals in it solution that trigger the positive negative polar on the surface. Then the whole process will started. Then it will end after there's no more charges in the environment. So the first condition when we talk about Aquarius or talk about corrosion, then we will start with environment. Okay. Now the next question is that how do we measure? How do we measure? I think I missed out one. Okay. So environment here. This is just you can read from here. All right. So another one is that what tools that we can use to evaluate the theoretical activity. Okay. We will be using pH diagram or potential pH diagram, or another word for pH diagram, we call it Paul-Bloch's diagram, right? Or pH diagram, which is, you know that this, if you have a combination of these two, means your y-axis consists of voltage, and another one, x-axis will be contribute. You can plot a pH value on the x-axis. So this is y, this is x-axis. So later I'll show you one sample what is pH diagram. Or if you look online, if you need to look more detail about pH diagram, then another keyword they can search is Paul-Bloch's diagram. Again, this diagram is for theoretical activity. All right, and this is a reference value when you want to calculate something. Okay, in the real case, this one only can be this diagram only can be a starting point for your analysis, and a real case happen in the practical. You need to go to the site and then collect all the parameter on site. Then you do add-on analysis on that. So this diagram only a starting point for theoretical value. It's a theoretical value. Because when you use this pH diagram, you need the input from environment. So when you use the pH diagram, you need input from environment so that you know what is your pH value, you know what is your E value or energy value, okay, or voltage value, right? So later I'll let you see what is pH diagram, okay, all right. So these are the basic idea how we start to look at corrosion and how do we do analysis on the corrosion. So these are the two introduction for how do we analyze corrosion. Next. So I give you a simple diagram on the left hand side. So as you can see here, the gray area, the far left, the rectangular, that one is we assume we're having a metal material. Okay, we have a metal material, and this is a simplified model. So what happened during the corrosion? You'll be seeing some ion coming out from the surface of the metals, and some hydrogen ion attracted to the surface. And then you'll see some electric current or electron charge moving from one end to another end. Okay, so this is how you start to explain corrosion using electrochemical process. Okay, so when you start to explain about corrosion, you start with this diagram, right? Metals, and then there's no extra additional electricity supply. Everything happened with metal and environment. Okay, so we start to look into step by steps how corrosion happen. So just now in the introduction, we mentioned that we need to look at environment. And in this chapter 2, we look at specifically on the Aquarius, means that we look at solution. The environment is a solution. At the medium around the metals and alloy is liquid. So it's a solution and liquid. And the most common medium is water. Okay, the most common medium, if you live on Earth, most common medium for corrosion is water. All right, so you can see all this corrosion happen in any contact surface that link with water. Okay, these are all the example, right? Heat exchanger, waste transport. Waste transport, the most obvious one is the lorry truck for the collecting the rubbish every morning. All right, so you can see that they will sure have corrosion part on the trash called the trash bin. All right, so this is the one. So we start with water, and then what happens if we have water and metals put together? So we will specifically focus on, we will start with water and metal, or more specifically, we use ion, right? So what happens if ion and water, they mix together? Okay. Or the word Aquarius itself, Aquarius means solution, corrosion that happen in a solution. And it not only happen with water, it can be acidic, it can be acid, it can be alkalic, and so on. But you know that corrosion is very, very active in the acidic environment. But we start with water first. All right, now let's look at iron-based alloy. What happens if you put iron-based alloy or iron in the water? So like what the schematic diagram on the left, then we start explaining the Aquarius activity, Aquarius corrosion activity in the water. First, You know that corrosion, when corrosion happens, you will create a positive charge and negative charge, or positive polar and negative polar. So at the anodic area, what happened in the anodic area or the negative polar? Anodic area, you will see that the ion Fe start to release or start to break itself into ion, right? Ferrum, you'll break from its structure, you will break into structure, become ion, and it will contribute to electron. Okay, so we start with what happened to the ion side. So we will create the first one. The process start from ion, ion Fe to become a positive charge and contribute electron. That's why you see on the top there will be a hole happen at the surface. So that's why corrosion definition is one of the keyword in corrosion. We mentioned the destruction of structure. That we use the destruction because there are some missing element on from the surface, right? So how the ion missing from the surface, it become ion. Okay, so when you explain about corrosion, you have to be careful that it's not missing of molecule. It's not missing of a physical granular. It's not a physical particles, but it become charge, right? Metal become charge. Okay, so I label on the schematic diagram there. So you have a negative polar, or you have an anodic area, where anodic area is an area where it contribute negative charge. And yeah, okay. Then when corrosion happen in the metals, the rate of corrosion is controlled by another area. So you have anodic, opposite of anodic we call cathodic area. Okay, so remember that the rate of corrosion is controlled by the cathodic reaction or positive polar and not anodic area. Okay, so just have a clear understanding on the rate of corrosion. Where does it happen? The rate of corrosion controlled by cathodic polar or cathodic reaction. What happened in cathodic reaction? Cathodic reaction, it bring hydrogen charge, positive charge, combined with the electron. You have to ask where do you get electron from? It's from the metal itself. So it combined when the positive charge, hydrogen, combined with negative charge. These two you learn in thermodynamics or you learn in material science. This one, positive charge, negative charge combined together, it become hydrogen molecule, right? Become H2. So this process, right? So from today onwards, because later we'll look at another chart that will describe the rate of corrosion. Rate means how fast the corrosion happens. It controlled by cathodic reaction. And what is cathodic reaction? One of the simplest example is hydrogen. How hydrogen generated in the corrosion process is a combination of positive charge of hydrogen plus electron negative. And you have to understand where do you get this negative. 2 negative is not from external electricity supply, but is from anodic area. Okay, so you will see something come out from the surface and something deposited, or something that will you'll see bubble. You'll see bubble near the surface because the bubble is hydrogen. Okay, so far, by looking at this diagram from these slides, basically you have some idea what is aqueous corrosion about. Okay, any questions so far? How aqueous corrosion with water in the case of iron and water. Okay, some keyword I highlight on these slides. What is anodic? What is cathodic? Anodic means you are creating negative charge. And cathodic means you receive charge, or you have a positive polar, right? You combine with the negative charge, become something. Any questions so far?
No, sir.
Okay.
Yeah, no, sir.
All right. Let me check attendance. Okay. Logeswaran, you are here? Logeswaran, morning.
Yes, sir. Morning, sir.
All right. All right. Now, just to fresh back, what is periodic table? So we're not going to go through deep into this one, but it's just to recap what you have seen before. Okay, this is periodic table, and on the left-hand side, you see how you read the periodic table. You have 1, 2, and then column 3, 4. 1, 2, and then 1, 2, 3, 4 right here, and then 4, 5, 6, 7, 8. Right? 4. This is yeah. So basically, what you see in periodic table on the left-hand side, from here, from left-hand side, is all metal. Okay. So the example we use is ferrum, with this one. And of course, you see aluminum is here. So aluminum will be a bit special. So you need to know how to read the periodic table, right? So the tendency to receive electron, the tendency to break and contribute electron, you have to be careful when you look at a periodic table. Okay. Again, this one is already covered in other module. This is just a introduction, or just to recap what have you seen. Huh? Okay. We also explain why ferrum become too positive. And again, ferrum or ion molecule, you have you learned in material before. Ferrum, you have ferrum 2, ferrum 3, right? Ferrum 2, ferrum 3. So later you will see ferrum 2 and ferrum 3 in our calculation. All right, let's continue. So just now we dip our metal in in water. Another one is we look at acidic solution, meaning it still fall under aqueous category. But what happens if we dip into metals? Dip acid into metal into acid. So if you compare acidic solution and alkaline solution or neutral solution, acidic solution will contribute the corrosion will happen faster. Okay, so this will be the difference when we talk about prevention later on in later chapter. Okay, so if you have an acidic, then you need to change the pH to become alkalic or neutral. And just now we mentioned about cathodic reaction that we mentioned in the previous slides. Cathodic reaction is where it controls the rate of corrosion. So if you, the more active your cathodic reaction on the surface, then it will be accelerated. The process will be faster and faster. And in this case, what happens if you have an oxygen? Just now, we only talk about electron. So we only show you from electron, and where is this electron is from metal itself. And this catalytic reaction, it control the rate. Now what happens if you add in, if you look at the environment factor, this is on the material factor, material dimension. What happens if the environment, you add in another one? So if you have oxygen, let's say this one, you have an oxygen around the metals, depolarization will happen. This one we mentioned before in chapter 1. So remember, in corrosion engineering, depolarization, you have to be familiar. What is depolarization, right? So depolarization is deal with oxygen. Huh? So this is what happened in catalytic reaction here, catalytic area. Just now we get hydrogen, right? Hydrogen plus electron. Then plus oxygen, we get water. Does it correct this equation? Can you check? Does it balance? Okay. So this equation is not balanced. Huh? What is the correct one? I'll give you maybe 1 minute to check this equilibrium equation. How should we write this equation? Now, depolarization, it involves oxygen and charge and hydrogen. However, the element is correct, but this equation is not in equilibrium, not balanced. Have maybe 20 seconds or maybe 30 seconds. Look at this equation, how to balance this equation. Yeah, so if you have an answer, you are welcome to give me your
So it
opinion.
should be 4 hydrogen plus 4 electron.
4 hydrogen, 4 electron, and then
O2 equal to 2 H2O.
2. So yeah, so the more correct one is you have to make it balanced, because why? Because here your oxygen only have 1, and on the left hand side in your process, your oxygen have 2 oxygen there. So this one is not balanced. Means we have a question mark, where is the other oxygen will go? So you need to balance this whole equation. All right. So look at your oxygen, because it's not balanced, right? Because if you look at here, yes, hydrogen you have 2, but oxygen is missing. All right. So you check your equation. Always check your equation. All right. So the correct one is 4 hydrogen positive, and it must be balanced. 4 positive, 4 negative, balance, and oxygen, 1 oxygen molecule, you become 2 water molecule. This process we call depolarization, and this process will accelerate the corrosion. All right, it will accelerate the corrosion. So as you know, Catholic earlier, Catholic in slides before this, catalytic reaction control the rate. And if you want to make the condition worse, you ask the help of oxygen to help you. You ask the oxygen, if there is an oxygen around the metals, then the process will accelerate, will happen even faster if you have oxygens around the metals. Okay, so depolarization is a concept that is important in corrosion. So in the test or in the final exam, if the question asks you about acceleration of corrosion, your answer, we are expecting you will write something depolarization and the process, okay, and the equation. So just be careful when you write the chemical, electrochemical reaction. Okay, so this one you learned before in your chemical already. Yeah? All right, so this is just a side note. The oxygens will react with hydrogen at random rate on the surface. On the surface. It's not inside the metal, but on the surface. Does the process happen on the surface? It's not some distance from the metal, but the keyword depolarization happen on the surface. Right? So by having this definition, later when we learn about corrosion prevention, you have to come up with a solution that clear this issue. You're going to tackle the surface condition. Okay. All right. The next one, we talk about oxidization reaction. So the first reaction that we learned just now, at the cathodic area, metals break into ion and give electron. And just now, the depolarization process, where you combine hydrogen, electron, oxygen, you get water. Or how you memorize it is depolarization. Normally you will get water. Where you get water is because of the oxygen. All right. And how you get oxygen is because from the electron in the metals. How you get electron is from the ferrum. And how you get the water hydrogen is from the solution itself, H positive. Right? So by combining these two, and there is an internal process, right? There's an internal process where when this process happens, because this process happens randomly in the solution, which is between the metals and the solution, and this happens on the surface. So this process, there is a process happen in the middle. So I use the double arrow here, where the water molecule will changing from charges back to molecule and back to charges and back to molecule. So this process will happen back and forth depending on the environment you have. Okay, so this one, just take note that this water, although depolarization, yes, the equation give you water, but you have to know that this water actually keep changing phases from molecule to charges. And if you break water, that you learn in chemistry, if you break water, you will get hydrogen positive charge and OH negative charge. All right. So you have how you get H positive, you break from water. Sometimes you get from water. Sometimes you get from OH. Then you combine with the knowledge you know from this one. You know that the water interfaces, or the water keep changing phases from charges to solid. And sometimes this one, the H positive, will go into depolarization process. Okay, so this one sometimes will go into this equation and contribute more water, and the cycle will happen like this. Okay, yeah, all right. So so when you have a water solution, you put metal in solution, so that's why corrosion happen quite fast if there's a water exists around metal. Okay, so these are the simple electrochemical equation. All right, then you have three process here. 1, 2, 3, 2 main, and this one is just the intermediate process. So you combine 1 and 3, maybe a little bit more from here. You will get ferrum plus water plus oxygen. You will get a new products if you combine metal water, oxygen, you will get something called ferrous hydroxide. Okay, ferrous hydroxide. And here you get 2, right? Later you will see 3. Here you see 2 means this is the ion 2. You know that ion you have a few types, right? You have ion 2, ion 3. So if you see 2 at the back of the bracket, means that if you need to combine, you need to balance the molecular electrovalence, right? So when you balance this molecule or this this molecule, when you have 2 here, means you are referring to ferrum 2. Okay, when you are having ferrum 2, a scientific name we give to this FeOH2 is ferrous hydroxide. Okay, so just recall back, OH2 is hydroxide, and OH2 means 2 oxygen, 2 hydrogen. You combine together, you get hydroxide, and this is ion element. So you know that ion they have phrases, right? So the shape of the ferrous you change name. So when you combine metal and the OH2, you only can meet ferrum 2. So when you have a ferrum 2, then we give a name of ferrous hydroxide. Just put a note in your personal note there. All right. So here, it just show you how ferrous hydroxide happen. Okay, how ferrum hydroxide happen, and this ferrum hydroxide sometime will happen this process also. Means sometimes this one will be in the hydrous form, means the ferrum itself, it will go and combine with water, and you have FeO means ferrous oxide, single O means oxide. This is a chemistry name. If you have single O, single oxygen, mean oxide, and then this is ion metal, so you have a ferrous oxide. Combine, there's a dot there. Dot means you partner, means you do not combine, but it's just a valence, electrovalence attachment. So you have attached with water molecule, means inside the water, around the water molecule, you will find ferrum oxide. Or, because if you balance the chemical reaction, right? So what is hydroxide? Hydroxide, you have 2 oxygen, 2 hydrogen, right? So here also, you have 2 oxygen and 2 hydrogen. So this one is quite a naughty molecule. It can change form either this one or this one in corrosion situation. So in corrosion situation, when you combine ferrous or metal, so metal times water times oxygen, then you either you get this one or you get this one. But normally we will just give it this term because you will see this one on the surface of the metal. Okay, those you are not see just above the water, you will see FeO dot water. Okay, those deposited on the surface of metal, you will get FeOH2 or ferrous hydroxide. Okay, so this one you can read lah. Okay, so this explains how oxidation happens on metal surface. This one with the help of oxygen. Okay, next one. So again, FeOH2 The name is ferrous hydroxide. So I just put it there because sometimes I also confuse the name of Fe3OH3. So I just put here ferrous hydroxide just to remind myself. All right. So we have done with the chemical process. Now we look at another dimension of environment, which is the pH value. Now we know that if you created a new compound, a new chemical compound, especially in water, it will give you, especially hydroxide, OH, OH something. So OH something will give you a pH property. So for ferrous hydroxide or ferrum 2 or iron 2 hydroxide, the pH is 9.5. Okay, pH is 9.5. Let me ask a simple question. Let me ask someone from the class. Rogesh Warren, are you there?
Yes, sir.
So if you look at value 9.5, what does it tell you? If your pH value is 9.5, what does it tell you?
It's more alkalic, sir.
Alkalic, all right. So we just, all right, good. Right now, just now we mentioned that if you have an acidic environment, then it's going to accelerate the corrosion process. So this process, ferrous hydroxide, if you measure this, only this element, it gives you alkalic pH value. Okay. So if you go to the corrosion site with pure water, but of course, this one only happened in the lab condition because in the real case scenario, you won't find pure water. But in the lab experiment, if you dip ion or metals in a pure water, you can find ferrous hydroxide after a few days. You left over in the tube, then you test the water, you'll find that the pH change from, the normal water, pH water is 7, neutral. You'll find that the pH value will change to something near to alkalic, right? So this is the textbook value, right? But the concept is that you have to know what happens if you dip metals in pure water. So the one of the answer we expect is you should explain about the pH value. pH value, we won't expect you to give us the exact number, but you should say something that it will change towards the alkalic pH value, right? So this is one of the point that we talk about ferrous hydroxide, or what happens if you put the metals in water with the assistance of oxygen. Okay, all right. So let's look at one video that give you some idea what is ferrous hydroxide. Okay, however, this one it add with acid, so that the reaction is significant. The color is significant that you can see. All right. So let's watch this.
Upon addition of sodium hydroxide, iron 2 ions present in the solution react with hydroxide ions to form iron 2 hydroxide, which precipitates from the reaction mixture in the form of a green solid. This precipitate does not react with hydroxide ions, so adding excess sodium hydroxide does not cause the iron 2 hydroxide to dissolve.
Okay, now just now the video show you the color of ferrous hydroxide. Okay, later I will show you another video what happens if you have a ferrum 3 OH3, right? The color will be different. So now I'm showing you the condition when you mix metals, you mix water, oxygen, you get something like this. Of course, this video is using acidic solution, but you still see the main key that I want you to focus on is on have an idea what is a ferrous hydroxide and what is the color of ferrous hydroxide. Right, just now you see the color, right? Okay. Now this is a side note for you when you do revision. Ferrous hydroxide, or FeOH2, when it's in pure form, it is in white color. However, in the video just now, you can see that the color is greenish black or green when there is an oxidation process happen. Okay, so this is the general idea or general concept of why in the corrosion site, or when you go and inspect things that corrode, you will see different color, right? Or why this site I see greenish color. When you see greenish or greenish and black that you see in the video, the color that you see in the video on the surface, it means that oxidation happened, and very high possibility you are seeing ferrous hydroxide. All right, so at least by observation from the surface, you can estimate what is the element on the corroded surface or corroded site. Okay, so today onwards, I already tell you what is the color. I already tell you the process. So at least you can explain to people when you see a corrosion spot or corrosion site. Okay, and just remind that ferrous hydroxide, the pH value is 9.5. So just now in the video, if you add acid to ferrum, when you get ferrous hydroxide, acid and alkali you combine together. Basically, you reduce the acidic of the solution when you mix with ferrum, mix between ferrum and acid solution. Okay, all right. A few more slides, then we call it a day. Okay, all right. So I just give you some idea. I draw something on the schematic diagram just now. I give you a green color to represent ferrous hydroxide. Okay. Now, sometimes you will see ferrous oxide just now, FeO, convert to ferric oxide or ferric hydroxide. Okay, so this is another process that could happen at the corrosion site, and this normally you will see if the corrosion site was left in the long period, you will have this process, right? So this ferrous hydroxide, the green color one, will combine with water and oxygen again. So this process will continue to happen. If you leave the surface long enough in water and with the presence of oxygen, this element is going to change to another new element with FeOH3. You see this change the chemical formula. Although we didn't write anything here, but just now I mentioned OH3 combined with ferrum or ion 3 charges. Okay, so there's a name there. Okay, again, check the solution. I purposely put this wrong equation just for you to check how to balance this chemical reaction. I will ask this question to Sivendra. Okay. The rest of the class, you can try to look at this equation and try to double confirm Sivendra answer. Okay, I'll give you maybe 1 minute to look at this equation and give me what is the correct equation. Okay, those watching on YouTube, you can fast forward 1 minute ahead, or maybe if you see the screen change, then you can continue to watch the video. Sivendra, you are there? Are you there?
Yes, sir. I'm trying to solve it now, sir.
Okay, good. The rest you can try to look at the equation and how to balance. The element is there. The element is correct. It's only the equation is a little bit not balanced. Means something different. If you look at left and right hand side, something missing. All right, one side is too heavy, or another side is out of balance. I give you hints. When you check electrochemical balance, start with oxygen. You can start with oxygen, or you can start with hydrogen. My personal preference, I like to start with oxygen. Okay. You balance the oxygen both sides first, then you will see how you balance the rest. Okay.
So it should be 4FeOH2 plus O2 plus by 2H2O should give you 4HeOH3.
Correct. All right. So again, my personal method, I like to start with oxygen. You can start with other element, but I like to start with oxygen. Okay. So the correct one is 4 ferrous hydroxide, or FeOH2. Water is correct, oxygen correct, and this one is 4. Okay. So always check. Sometimes I'll have a typo error in my slides, so you help me to check. Okay. Yeah. So sometimes I purposely put some mistakes there, right? Just to see whether you can see the mistake or not. Okay. So this one, this normally, why I put this one, because this also one of the area where students make mistakes. They just give me the element, but the chemical process is not balanced. Okay. Yeah. All right. So today we focus on metals, water, and how all these chemical compounds can happen. So when you have this process, again, what is the name of this one? Huh? So there's a name for is the name for FeOH3. So so this just now. So let's watch a video. This color, you know that this color is this one, right? Just now in the video. So we will see this color is this one. Huh? So let's watch this video, and if you go online, look for answer. Sometimes the Fe, they use ion, and bracket 2 or ion bracket 3 accordingly. And again, to make the effect so obvious, to make the visual effect, I use the video using acidic solution or acid, right? So that's why you'll see all this very fast. If not, you have to wait a few days to see all this color, right? So let's watch the video. This one is this one. This one is this one. Okay, so previously, as a very short video, you'll see that when we add the hydrochloric acid, a sodium hydrochloric or acidic solution into the ion solution, you see you have two color. Okay, so one you get ferrous oxide hydroxide, one you get this one iron 3 hydroxide. Okay. So, oops. So this color is what you see in the common corroded area. Okay, so as you can see here, when you see this color, you know that this happened. When you see this one, you see that, you know that this one, how you get this one is from here, right? When you mix this one with water and oxygen again, you will see this one. So this one is orange color or brown color. Okay, so you see that this is the by process or a process from this one. Okay, so in the corroded side, you see you have two color there. Okay, so I put a remark there. So this one, there's a name for FeOH3 is ferric hydroxide. I put a wrong name there in my slides. Green color is ferrous hydroxide. Orange color will be ferric hydroxide or hydrous ferric oxide. Okay, so means that the green color ferrous hydroxide can change color to orange color when you mix, when the process further with water and oxygen. Okay, there's a wrong color I put on my slides. The ferric hydroxide should be orange color. Okay, by just illustration, just illustration that the green color can change to orange. So ferric oxide, this one orange color, have two group of products. One is magnetic, one is non-magnetic, one is magnetic. By the word itself, you know that what is magnetic, what is the magnetic mean, right? Magnetic means if you put a magnet near it, you're going to pull the element near to the magnet. So non-magnetic means even you put a magnet beside it, it will not do anything. Okay, so you have a non-magnetic component and magnetic component. This is more on the chemical. So for those non-magnetic one, we call it hematite or alpha HeO3. Same, also alpha FeO3, but another type is magnetic. So you have two types of alpha FeO3, or you can call it right. So this ferric hydroxide, inside this ferric hydroxide, all right, again this ferric hydroxide, it can interchanges, it can change to ferric oxide in the solution, then it can come back to this one. So when it change in the hydrous ferric oxide condition, you have two. One is under non-magnetic, one is magnetic characteristics, right? This is a constant value, the alpha form, have a greater negative free energy formation, meaning you have more stability in terms of thermodynamics. All right, so non-magnetic, you know that it do not have any reaction when you put a magnet near it. So when it's don't have reaction with the magnet, means there's no electromagnetic wave compared to this one. So we will call this one as a more thermodynamic stability compared to this one. Both also alpha FeO3, but the non-magnetic one, right? Oh, sorry, it should be if you have a FeO3 with the alpha, means it will have a greater thermodynamic stability compared to other solution. Sorry, not between these two. Sorry, just now I've explained between these two. So this one is, if your FeO3 with the alpha means it's more stable thermodynamically. Okay, so you see here, I put a side note here. Ferrous oxide, what is ferrous oxide is FeO and water. So if your FeO change to FeO3 with the alpha, means it will thermodynamically stable, right? In the material module, when you have the material chart, you can see that the ion have alpha phase, beta phase, and gamma phase. So when you have a gamma phase, means it will be more stable thermodynamically. Yeah? So this is just a side note lah. The color of hydroxide. Okay. Now the differences between FeO3 and FeO2. Okay, FeO2 and FeO3. FeO3, the pH value is nearly neutral. Okay, it's nearly neutral. Just differences between FeOH2 and FeOH3. FeOH3, if you have more number here, it gives you more neutral. And you have OH2 or Fe2OH2, it will be more alkalic. What is the color of Fe3O4 times water? This one, we call it ferrous ferrite. This one is a black color that form between Fe2O3 and FeO. Okay, so we're not going deep into how this form, but the one that I show is a more major products that you will see in corrosion. Okay, so by looking at this statement, meaning at a corrosion site, Aquarius corrosion site with metals, water, and oxygen, normally you can find 3 layers. If you cut the corroded layer sideways and put under microscope, you can see that you have a 3 layer of iron oxide in the different seats when you have an oxidation process happen. Okay, so you have FeO, Fe2O3, FeO, and Fe3O4 with black color. Okay. Yeah. So this lah. All right. So I think we stop here. Okay, we stop at these slides. Then I will see you in the next lecture. Let me stop the recording.